bits. So, reactions of alkenes. Alkenes have a greater reactivity than alkanes. Why is that? Why do alkenes have a greater reactivity than alkanes? It's because of this high electron density double bond. It's because of the fact that alkenes have electron density above and below the plane of the bond. That means that the electron density is spread out and it's more accessible by nucleophiles or things that are, electrophiles, things that are attracted to areas of high electron density. So this is due to the high electron density of the carbon-carbon double bond. No, actually, I'm going to be much more specific than that, of the pi bond. It's the pi bit of the double bond that's important. Sorry, I'm going to be specific because that is key. So, and again, I'm just going to scribble this out because it's technically the pi bond. The pi bond bit, so just, I would change that in your notes if you haven't already, the pi bond bit, just so we don't introduce a misconception. The pi bond has a lower bond enthalpy. So the pi bit of a double bond has a lower bond enthalpy than the sigma bit of a double bond. That means it requires less energy to break. Hence, the double bit of a double bond is easier or more reactive than a single bond. It's also, a pi bond also has a higher electron density than a sigma bond. Hopefully, understandably, because you've got 4 pairs of electrons associated with a carbon-carbon double bond. So near to the pi, where the pi bond is, than you do in a sigma bond. If we think about the carbon-carbon bond strength, so carbon-carbon bond strength for a single carbon-carbon single bond is 347 kilojoules per mole. The double bit of a double bond, no, I lied. The whole of a carbon-carbon double bond requires 612 kilojoules per mole to break the whole of the double bond, but that's because it's made up of 347 approximately, which is the sigma bit, and 265, which is the pi bit, the double bit of the double bond. So actually the double bit of the double bond requires less energy to break than a sigma bond does. Alkenes are also attacked by electrophiles because of this high electron density. Electrophiles, which are electron pair acceptors, again, another definition you need to learn, and they're obviously attracted to the area of higher electron density, which is present, the area of higher electron density present in a carbon-carbon double bond. Some examples of electrophiles would be things like bromine, HBr, what else is going to accept H+, etc. Electron pair acceptors, you need to learn that definition as well, because you need to be able to recall it in an exam. That's what they're looking for. Okay, let's think about electrophilic addition then. Addition reactions are the bonding of 2 or more molecules to form a single product. That's how we can work out if something is addition. You're combining 2 things to make one product, or more than 2 things to make one product. So for example, polymerization is technically an addition reaction. Addition polymerization with alkenes is an addition reaction. It's addition polymerization. You have actually got condensation polymerization, which produces another product, a second product, so that's obviously not addition. Okay, so for alkenes, this means that the pi part of the bond is broken to form a saturated organic molecule. For example, let's look at a general equation for an unknown alkene. Let's just do normal electrophilic addition. So let's add something across the double bond, we're going to end up with our species with X on one carbon and Y on the other. This is an example of electrophilic addition. We could actually, yes, okay, good. Yeah, no, I'm going to leave it like that, sorry. I was going to be more specific, but I'm not going to because we are low on time. So we have added X and Y across the double bond to form our product. Fabulous. If we wanted to be, let's be a little bit more specific here, with hydrogenation. What's hydrogenation? Hydrogenation. It's adding hydrogen. Hydrogenation is adding hydrogen across a carbon-carbon double bond. What are the reagents and conditions needed for hydrogenation? Well, obviously, we're going to need hydrogen because you have to have the hydrogen you're adding, but also you need heat and a nickel catalyst. And that is a catalyst. So again, I'm going to just do a super quick example because we are low on time. And, you know, I like talking too much. If we add hydrogen across ethene, we're going to end up with ethane. We have added hydrogen across the double bond. What about if we add something a little bit more interesting, so something that's not symmetrical, like water? Technically, water actually is a symmetrical molecule, but it doesn't split symmetrically, sorry, when we are adding it across a double bond. So what actually happens? What reagents and conditions are needed to add water across a double bond? Hopefully we know. If not, get it on your synthesis map and learn it. So we need high pressure, high temperature. I know it's not that high a temperature, but it's a decent high temperature. You need heat. And an acid, for example, H3PO4 or H2SO4, something like that. Excuse me. And again, I'm just going to keep it really simple because we're running out of time. Let's take ethane, and you're going to need your water, obviously. Otherwise, how are you going to add water across? And this time, water splits into a hydrogen on one side and an OH minus on an OH on the other. So you end up with, in this case, an alcohol. We add the hydrogen on one side of the bond and OH on the other. In this case, we've got a symmetrical alkene. So we're going to produce, it's easy to work out what the product is going to be. We will, in a second, think about what happens when we have unsymmetrical alkenes. That's what I want to spend a little bit longer on. What about if we add a halogen, for example, so X2, so for example, bromine, Br2, chlorine, Cl2, etc. What happens? All we need to do is add the halogen itself. So we don't have any other conditions needed to add. Let's add chlorine across our double bond. And please, when you're doing it, hopefully you'll have a little bit more time. Try and keep your drawings a little bit neater than mine. Mine are not neat enough, really, because I'm trying to write quickly and think at the same time. Sorry, I think and talk at the same time. So, no, actually, okay. Apologies. I'm just going to give myself a little bit more space, and we're going to compare it to the next slide. So I will do it a little bit better than this. We'll think a little bit about the mechanism here. So what's going to happen when you have got, I did do chlorine, didn't I? Oh, I'm going to do bromine because that's the more common one that you're expected to do. It's not the only one, but it is more common. So I might as well do it and then you've seen it. So what happens when you've got, for example, bromine or a halogen that approaches a double bond which is an area of high electron density? You've got an area of high electron density, that's lots of negative charge around that double bond. What's going to happen to the bromine? It's going to polarize that bromine bond. It's going to induce a dipole. technically that dipole could happen instantaneously. It could have been an instantaneous dipole that formed, but actually it's much more likely that it's going to be induced, because one of the bromines is going to be slightly closer to the double bond than the other, and that's going to repel electrons away from that bromine towards the other bromine. So you're going to get an induced dipole. Induced dipole. Hopefully I haven't got in the way of myself in a second. Again, now how we're thinking about how these two things are interacting. We've now got a charge and we've got an area of high electron density. So the electrons are going to be attracted to the positive thing, and that's going to cause the electrons in that bond to move across to belong solely to the single bromine. That means we're going to end up with our intermediate species. Now, suddenly I've got a carbon with only 3 bonds. If a carbon has only got 3 bonds, it therefore is missing possession of an electron. That means it will have a full-on positive charge, must have a full-on positive charge. I haven't given it enough energy to exist on its own, and there is a deficit of an electron because that carbon is missing an electron. So it will have a full-on positive charge, and we also have a bromine over here, which has got a full-on negative charge because it gained possession of both the electrons in the bond when it only owned one of them. It had only one of them that was associated with it. Now what happens? We've got a positive and a negative. The negative electrons are going to be attracted to the positive charge, so they're going to move up. I've slightly got in my way there, and I should really point it at the carbon if I'm being correct here. Let's go straight at the carbon. There we go. And then we have got our dihalogenoalkane. Again, this is with a symmetrical alkene. So the carbocation intermediate that's formed in the middle, this is a carbocation. I won't draw that arrow because that is confusing. That is my carbocation species. If the bromine, I draw the bromine on the other carbon, it would have made a difference. The carbocation would have been identical. I just would have been drawing it from the back instead of from the front or whatever. They are identical. It doesn't matter because my alkene is symmetrical. Those carbons are identical, and therefore it doesn't matter which one the first bromine goes on. The second one it will always produce the same product, sorry. How can I test for the present, let me rephrase that. This reaction is how we test for alkenes. Sorry, I have written my induced, I thought I might have done, let's get that out of the way. Induced dipole. So bromine solution is used to test for unsaturated compounds, i.e. alkenes, because alkenes decolorize the brown solution. So it goes from orange to colorless. Oh, not orange, from brown to colorless. I think actually you can say orange. Orange to colorless if there is an alkene present. Because bromine is added across the double bond, that takes the brown/orange bromine out of solution, leaving us with a colorless solution. Okay. If we've got a hydrogen halide, it's the same as we've done before. I'm going to speed through it ever so slightly because I don't want to run over too much. So hydrogen halide, that means we've got a hydrogen and a halogen bonded to one another, so HX. If you have got a hydrogen halide, we have already got the dipole present. So it's the same as it was previously, it's just we already have a dipole. So you've already got the partial positive charge because a halogen is going to be much more electronegative than a hydrogen. It's going to attract a pair of electrons in that bond. So you've got your partial negative charge on the bromine, partial positive charge on the hydrogen. That means you can get the attack of the double bond immediately. You don't need to induce or wait for an instantaneous dipole to appear because it's a permanent dipole. I'll write that in a second. What am I doing? So then we end up with, now we add the hydrogen first, because that's the thing with the positive charge. That's what was attracted or attractive to the high electron density in the bond. Again, though, we've now got one carbon which doesn't have all of its electrons that it should have around it. That means it's deficient. So it will have a full positive charge, but we have got a little bromine that has got a full negative charge. How are they going to interact? Funnily enough, you get the attack of the electrons towards the thing that they're attracted to, the positive. That's what causes the reaction, and you end up with the addition of the hydrogen halide across the bond. Here, let me just make sure I've written it in. We have got a permanent dipole though. Okay. Just as an aside, hydrogen halides tend to be gaseous under standard conditions, so they tend to be bubbled through the reaction mixture. So if you're talking about practicals, or if there's a practical question, you would talk about bubbling the hydrogen halide through. Okay. Now, I kind of wanted to have 10 minutes to do this, but never mind, we will have 5. We're going to think about asymmetric addition, or addition to unsymmetric alkenes. So when the alkene is asymmetric, it means the carbons are no longer identical. They've got different environments. If they've got different environments, they will behave slightly differently. This therefore means we can get 2 possible products formed. So if we have an unsymmetrical alkene, such as propene, and we add HBr to it, you've got to also be adding something that's asymmetric as well, of course, because if I added bromine, it wouldn't matter which way around the bromines went, they're identical. So HBr, so the hydrogen bromide, so that I've got 2 different atoms, so the products are different. You can see the products are different because here the bromine has been added to the central carbon, but on the right-hand molecule it's been added to the right-hand carbon. So those 2 molecules are different. When you do this in a laboratory, you'll find you have a mixture of products, but one will be in majority. One will form most of the product, and then there will be some that is in the minority. And which is which comes under Markovnikov's rule, which is spelt differently in all the different exam boards, which is great fun. But oops, we've spelt it like this. So this can be explained using Markovnikov's rule. What is Markovnikov's rule? Can we remember? How do we determine which is going to be in majority and which is going to be in minority? When you think about it, you've got to think about the process by which they get there, the reaction mechanism that takes them from this reactant to the product. Let's think about it here. In each case, you're going to get the attack of our electrophile, which has got its permanent dipole on it. Now, you could get attack via one carbon, so where one of the carbons bonds to the hydrogen, or you could get attack where the other carbon bonds to that hydrogen. That's going to form a different intermediate. That's going to form a different carbocation, because if we attack via the, and I'm going to make sure I get it the right way, the green route, let's go via the green route, we end up with a carbocation where the hydrogen has attached itself to the end carbon. So we end up with a carbocation where the charge is on the central carbon. That central carbon has got 2 alkyl groups attached to it. That makes it a secondary carbocation. If it's a secondary carbocation, it means it's got 2 groups attached to it. Both of those groups can give electron density to the carbocation. If it goes by the orangey route, the hydrogen attaches itself to the middle carbon, then the carbocation formed is on the end. If it's on the end of a chain, it's only got 1 alkyl group attached to it, it is a primary carbocation. Which is more stable, secondary or primary carbocations? Which are more stable and therefore which are more likely to form? If they're more stable, they're going to be more likely to form. Which one? Primary or secondary? It's going to be secondary. because it's got 2 alkyl groups to stabilize that carbocation and not just 1. Secondary, primary. Okay, when alkenes undergo electrophilic addition, an unstable carbocation intermediate is formed. Markovnikov's rule is explained by considering the most stable carbocation that can be formed. Alkyl groups, so carbon-based groups, are electron donating. That means because carbon is not very electronegative, it doesn't hog electrons. So if something is requiring electron density, it allows the electron density to be stolen from it, to be given to it. Alkyl groups are electron donating. The other phrases you might see are that they have a positive inductive effect, as in they allow electron density to be inducted away from them. Or you might see people saying that alkyl groups help to spread out the charge. Again, it differs slightly for what they will accept for different exam boards. So just double check for your specific exam board. Most of the time they will accept all of the definitions or all of the descriptions. But do just make sure that you're using the one that your exam board would prefer you to use, just so that you know you're going to get all the marks. Alkyl groups are electron donating. They stabilize this positive charge by spreading it out, by cancelling it out, or however you want to think about it. They stabilize this positive charge. If the positive charge is stabilized, that carbocation intermediate is more likely to be formed. Therefore, that is going to be the major product in this case. So this is going to form the major product. The more stable carbocation is going to form the major product, and the less stable carbocation will form the minor product.